All right, guys, welcome to our lesson 10. This is actually our last regular calculus lesson of the year. Hooray! The rest of this year is going to be devoted to AP review. So this is our last regular AP calculus lesson. So revel in it. All right, so we're going to be talking about volumes of revolution again today. Last time we talked about something known as the disk method. I didn't really use that language very much, but the reason for it is because we started off with a shape, right? And what we would do is we would rotate that around the x-axis, and the result is a shape that's a circle, and we call that a disk, right? So that's the disk method. The area of a circle, as you guys know, is pi r squared. So if you have a circle, and this is the radius, then the area of that circle can be found by doing pi r squared. You're like, okay, well, duh, Mr. Bailey. All right, cool. But I want to talk about a different shape today. I want to talk about a washer. For those of you guys who are familiar with tools a little bit, you know what a washer is. It's the thing that goes between a bolt and whatever it's being attached to. It's a disc with a hole in it, basically, right? Now the question is, how do you find the area of a washer? In other words, I need to find this area. How do I find the area of a washer? Well, you have to think of it as though there's two circles. You have the big circle, and that big circle has a big radius. And the area of that big circle is pi r squared. And we have a little circle inside of it. And that little circle has a radius as well. I'm going to give it a little r there. And the area of the little circle is pi r squared also, just with a different radius, right? If you want to find the area of the washer, you subtract the area of the little circle from the area of the big circle. So it's kind of like you start off with a full circle and you subtract this little piece out, and what's left over is the area of the washer. Okay? Now, notice they both have a pi in common, so I'm going to go ahead and factor that out. And we're left with big R squared minus little r squared. Okay? That's going to be handy for later on today. You might want to have that in your notes. So I would pause the video here and write that down. But there's the idea. This is what we call a washer. Now, yesterday when we did these activities and we did these revolutions, we created solids, which means that these were solid objects. They were not hollow at all. Today we're going to create volumes of revolution where they're solid, but they actually have some hollowness to them. There's some holes inside of them. So I couldn't find any good software this time that would generate them for me, so unfortunately we're going to be stuck with Mr. Bailey's efforts at just visualizing these things. So this next part, you don't really need to write this part. You can, but it's mainly just for you guys to watch. Now let's say I have two functions. Let's say one of my functions is the function f of x here. We'll call that f of x. And let's say I have another function here, which I'll make in red. I'll call that one g of x. And I'm going to have them both stop right about here on the x-axis. We'll call that b, and we'll call that starting point where they start a. All right? Now, let's go ahead and lie this object down flat. Now let's just do what we did yesterday really quick here. I want to rotate, let's start off with the green function there, the f of x function. I want to rotate that around the x-axis. So if I do that, my radius would be the distance from the x-axis up to that green function. And so I'm going to go ahead and label that now as my radius is f of x. Right? And if I were to rotate that around the x-axis, and draw that line very good though, it's not technically appropriate. Should be parallel to the y-axis. Slightly better, not perfect. All right, so there's my radius. All right, which is f of x, we'll say. Okay. Now, if I rotate that around the x-axis, I get a circle, and therefore the area of that circle is going to be pi times whatever f of x was squared. Right? We talked about that. And then if you wanted to do that all the way down, you're going to get like this little horn-looking shape here. And it would be a completely solid horn. Right? Now, let's back it up a little bit. What if I wanted to do the same thing but with the red function now? Well, if I want to rotate the red function around the x-axis, it's going to have a radius as well, and that radius would be just equal to whatever that function is. We'll call it the g function. Okay. Now, if I were to rotate that around the x-axis, it would look like that, and that would be pi g squared. So that would have its own little volume, right? And in fact, this one's going to end up looking a lot like a cylinder, actually, just because it's a straight line. There's no curving on it or anything like that. Okay, so we have two different solids now. But what if we rotated them at the same time? Okay, what if we rotated them at the same time? So in that case, then, we would have this big old horn thing around it, the red one. Okay. Now, the volume of the larger one was this. Well, to find the volume, though, we have to integrate them, though, correct? So I have the volume of the red one, I've got the volume of the green one. And they're both solids, so I have one solid inside of another. But what if I thought of this inside one as a piece that I wanted to subtract out? So in other words, it would create a hole inside of that horn shape. Well, then I would just subtract it. And now technically what you could do is you can integrate them together. With the pi out here from the starting point to the end point. And this is how you would find the volume of what we would call a hollowed out solid. Okay, so it has a solid with a hollowed out portion within it. Okay, so basically we're taking this area out and we're only finding this area here. Okay, and that's what we would call the washer method. It's for finding the volume of a solid that has some distance between the shaded region and the axis you're rotating around, because if you were to rotate this green section here around the x-axis, there's going to be a hole in it, and that hole is equal to the volume that G would have traced out if we traced it around there. Okay, so anytime your shaded region is distanced away from your axis of rotation, you're going to have a washer method. So now let's compare and contrast the disk method with the washer method. The real difference is does the shaded region touch the axis of rotation? So as you guys can see here, I've got this little shaded area. That's what I'm going to be rotating around the x-axis. And notice that my shaded area, it does touch the axis of rotation. The axis of rotation is part of the sides of that shaded region. So if you rotate this, you're going to get a solid without any holes in it. Now let's take a look at the washer method over here. Same shape, it's just been shifted up 3 spaces. But I still want to rotate it around, actually this time I guess we're going to rotate it around this horizontal axis here of 1. But as you can see, the shaded region's up here, and the axis that I'm going to rotate it around is not touching that shaded area. So if I were to rotate this shaded area around that axis, there's going to be a hole in a gap in the middle. Okay, and so that's whenever you're going to use this washer method, which would be this formula here. right? So we have two radiuses. You have a big radius and a small radius because you're going to have two functions that you're rotating. The big radius is the one whose function is farthest away from the axis of rotation, so that when you subtract them, you get a bigger number because it's a farther distance. The little radius is the function that's closer to the axis of rotation, so that when you subtract them, you get a smaller amount, or the distance is less. And as you guys can see here, this is really just pi r squared minus pi r squared, but I factored the pi out like I showed you at the beginning of class. We're just subtracting the inner area of the small circle from the outer area of the big circle, so we have a washer area, and then we're integrating it to create the volume of this solid with a hole on the inside. And so this is the process we're going to go through today. The only difference is that we're dealing with two different functions that we're rotating simultaneously and subtracting them to create a hole in the object that we're working with. So let's go ahead and jump into our first example. So we have our little shaded region here, as you can see. And I'm rotating that blue little shaded region here around, it looks like the x-axis. All right. So now we have two pieces that are going to be rotating around it. We're going to have this piece, which is this function right here. And then we also have this piece, which is this function right here. And when we rotate it, basically this red one's going to create the outer shell, and the green one is going to create the inner shell. And what we're going to have is we're going to have a hole in our solid that we're rotating as we go, because there's no area that's being rotated there. All right, and so that's the idea. So let's go ahead and begin here. Step one, we want to identify our big radius. The big radius is the function that's farthest away from our axis of rotation. So which line is farther away from the axis of rotation? Is it the red one or the green one? Well, as you see, that red one is farther away from the axis of rotation than the green one. So it's going to be the red equation, which is x squared plus 2. And we're going to subtract from that the axis of rotation, which is the x-axis. Now, when you're rotating around the x-axis, that equation is 0. Okay? So technically, if you want to, you could just simplify this as x squared plus 2. So there's my big radius. Now we want to find our little radius. The little radius is the same thing. We're still going to subtract it from the axis of rotation, but the little radius is the function that's closer to the axis of rotation, and in this case, that would be this green line. And so that green line is the equation y equals 2. So the little radius is just 2. And so we have this. So I have my big radius, and I've got my little radius. From here on out, I'm going to let this be called y1. And I'm going to let this be called y2, because we're going to be doing most of this on our calculator, okay? Now we're ready for step 2, which is where we're going to find the areas of these things and subtract them in an integral. So what you do is you take your big radius and you square it. And you subtract from that your little radius and you square it. And we're going to put a pi in the front. And that's like we're taking the big circle that would be created by rotating the red function and subtracting from it the green line, which rotate would create a hole in it, and we have this washer. And then when we're all done doing this, we're going to have this common little bell shape that we've been working with for a while now, but now it's going to have a hole inside of it, represented by this green shape. Okay, and that's the idea. But once again, on my calculator, I'm just going to be calling those functions y1 and y2. So this is what I'll be typing in to my calculator. Okay, and that's that. So if we type that into our calculator, if we type in this function for y1 and this function for y2, then when we put this into our calculator, we should get our final answer, which would be as follows. About 4.817. Okay, and I think I did forget to put my limits on there, so let me go back a little bit and put my limits back on there. When I did my integral, I forgot to put the limits of integration. We are integrating from x equals 0 to x equals 1. Okay, forgot to mention that, my bad. All right, so let's have you guys give one of these things a shot. All right, so go to your homework assignment and take a look at number 1 and answer this question on your homework, not on your notes. When you unpause the video, I'll share with you the solution to this problem. All right, so I've highlighted the red function there, negative x squared plus 6 on the line there. And also the green one is the one that's closer to the axis of revolution. So now you might be wondering, how can I tell which function is which? Well, at this point, I would hope that you guys can kind of tell which one is which just based on what you're looking at. I mean, this is a quadratic, right? And so that's the one that's shaped like a U. And this one is a linear, and that's the one that's a straight line that's diagonal there. So if you can't identify the functions, that would be a little bit of a problem. So you might have to get out your graphing calculator and just kind of see which one is which, graph them, and see which one is the right shape. But for the most part, I'm hoping you guys can tell just by looking which one is which. Now, as you can see, the red one is farther away from the axis of rotation than the green one. And so the big radius is going to be the red function minus the axis of rotation, which simplifies to this. And the little radius is going to be the green function minus the axis of rotation, which simplifies to that. Typing those things into your graphing calculator, I would just call this y1 on my graphing calculator, and I would call this one y2. And so whenever I went to go type this into my graphing calculator, I would have just had the following things there. Okay, now notice we are integrating from -2 to 1 because this is my leftmost point and this is my rightmost point. -2 is the x value on the left and -1 is the value on the right. Calculator should spit out an answer to you of this value there. Okay. Let's go ahead and take a look at another example. So on this example, our axis of rotation was the x-axis, but on our next problem, our axis is going to be a horizontal axis still, but it's going to be a different axis of rotation. So as you can see, my axis of rotation this time is up here, and that's at the line y equals 1. So let's begin example 2 here. So first of all, we have this curve here on top represented by this quadratic. Second of all, we have this line down here boxing in the shaded area represented by this equation right here. That's just the line y equals 3. The other two equations up here, x equals 0 and x equals 2, just tell you that we're going from x equals 0 to x equals 2. So we're staying in between those lines, which is essentially our limits of our integration that we're going to get to in a minute. Okay. Now, my axis of rotation is this black dotted line that you see here. So which one is closer to the black dotted line, the red line or the green line? Well, it's the green one is closer and the red one is farther. So since the red one is farther, my big radius is going to be equal to the equation of the red function minus the axis of rotation. Now this time my axis of rotation is 1. It's not 0, it's 1. And therefore my big radius can be rewritten as -x squared plus 6. My little radius of rotation is going to be the equation of that green line, which is closer to the dotted line, minus the equation of my axis, which is 1. And so now my little radius is 2. And on my graphing calculator, I'm going to go ahead and call this piece right here y1, and I'm going to go ahead and call this piece right here y2, and then I'm going to go ahead and move on to my third step where I integrate, just following our little formula that we're used to using by now. And there you have it. So let's go ahead and see what we get there. So just more practice, really. The only difference is that you're going to have a number here now, and you're going to simplify it. So, all right, so let's go ahead and have you guys try doing one of these now on your homework worksheet. Let's go ahead and have you guys do this problem right here. So go ahead and pause the video and see what you guys get. When you unpause it, you'll see the solution. All right, so there you guys go. I'll let you study that for a little while. You should have gotten 174.254. All right, let's move on to another example. So now we're going to switch our axes of revolution to become vertical instead. And remember, last time we talked about what does that mean whenever you rotate around a vertical axis? Well, that means you have to have your equations in terms of y, which we do already, and you also are going to be integrating with respect to y, which means that your limits of integration, instead of going from left to right, are going to go from top to bottom. So that's going to be our only two differences there. So we want to make sure that we're prepared to recognize that. But beyond that, there's really not that much of a difference there. So my radius is not going to be a function of x. It's going to be a function of y. My big radius is the one that's farthest away from the axis of revolution. So let's see if we can identify these. Now, what does this one look like? This is a square root function here, it looks like. Well, that's going to be the one that's curving right here, just like so. And then this line right here, that vertical line right there, that's going to be the line x equals 1. And both of them are rotating around this vertical axis right here. Now, which one of those are farthest away from that axis, horizontally speaking now, right? Because we're rotating this way. Well, the one that's farthest away is the red line. So my big radius, which is now a function of y instead of a function of x, because we're rotating around the y-axis, a vertical axis, is going to be the function, which is the square root of y plus 1, minus the equation of the axis. Now, the equation of the y-axis is just 0. Anytime you're doing an x or y-axis, it's just 0. Okay, and so my big radius is basically just the function itself. My little radius is going to be the distance of my green function from the axis of rotation. So my little radius will be equal to that green line, which is the equation x equals 1, minus the axis of rotation, which is 0. And so my little radius is simply the absolute value of 1. Once again, on my calculator, I'm just going to call this y1, and I'm going to call this y2. And we're going to be doing our integration here. Now, we want to know, what are we integrating to and from? Well, we're going from bottom to top. So that would be from 0 to 4. And it's going to be the absolute value of the y1 function squared minus the absolute value of the y2 function squared. And on our calculator, we're going to type dx, although really it's a dy, right? Because we're just assisting our calculator here in its understanding of things, but we know that we're really integrating with respect to y. So technically, we wouldn't want to put that there. But we'll go ahead and do it for now just for the calculator purposes. But you guys can go ahead and put y on your paper. Just make sure that when you type it into your calculator, you put a dx. Okay. All right. And so what would that give us as a final answer? I get 58.643. All right. Now let's do another example before I turn you guys loose on your homework there, because it's getting kind of repetitive at this point. So at this point, we want to do the same thing. I still want to rotate it around a vertical axis, but the difference is this time my vertical axis is not going to be the y-axis. It's going to be something else. So first of all, let's identify our functions. Which one do you think this one is? See if you can find it. It should look like a parabola, right? So that's going to be this guy right here. And I'm only going to highlight the portion of it that we care about. I mean, it's really this entire parabola, right? But I don't want the whole thing. I just want this much of it because we're only looking at the shaded region. And then see if you guys can find the next equation, y plus 2. Where's that one at? That's going to be this guy right here, right? But once again, we only want the portion that actually is on the shaded region. These other two blue lines, y equals 0, that would be this line here, and y equals 1, that's this one up here. The only reason they're giving you those to you is so that you know where to start and stop. We're starting at y equals 0 and we're stopping at y equals 1. Those are going to be the limits of our integration because we integrate from bottom to top. Okay, just so you know. Now, let's all, oops, I think I erased more than I wanted to. There we go. Now, let's ask ourselves, where is our axis of rotation? Right there. Now, which line is farther away from the axis of rotation? Well, the red one, once again, is farther away from that axis of rotation than the green one. And so my big radius, and this is going to be with respect to y, because we're doing a vertical axis of rotation. My big radius is going to be that equation for the red line minus the equation of the axis of rotation. So what is the equation of this axis of rotation? Well, hopefully you know it's x equals -1, but they are kind enough to just tell you right there. So we're rotating it around the line x equals -1. So it's the line farthest away from the axis of rotation minus the axis of rotation, so minus a -1. We can go ahead and simplify that, and we're going to get -y² plus 5. Now let's go ahead and do the green one, which is the little radius. The little radius has the equation y plus 2. Subtract from that the equation of the axis of rotation, and the double negative becomes a positive, so you end up with y plus 3. Okay. And at this point, we'll go ahead and set up our formula, right? We're going to have pi here. We're integrating from bottom to top because we are integrating with respect to y, correct? So we're integrating from 0 to 1. And it's the big R minus the little r. I decided to switch from doing y1 and y2 because I feel like it's a little bit confusing. But on your calculator, we're going to say that big R is y1 and little r is y2. So on your calculator, you're going to be typing this in, just so you guys know. Okay, that's for the calculator. But this is technically the way it should be written. And I didn't put my absolute value bars on there. But believe it or not, it really doesn't matter, once again, so long as you're careful to know that it's always the one that's farthest away that comes first, and then the one that's smallest that comes second. All right, so now I'm going to let you guys do your problems. I'm going to have you guys do 2 homework problems this time at once, and then I'll let you check your work against mine. Let's see. I'd like you guys to go ahead and do number 5. I'm going to shrink it a little bit here so we can see everything a little more clearly. I want you guys to go ahead and do number 5 And let's have you also do number 7. So we're going to have you guys do 5 and 7. 6 is just a repeat of 5, and I'm going to let you guys do that on your own for practice. So I want you guys to do numbers 5 and 7 right now. When you unpause the video, I'll show you my solutions. All right, so I'll let you guys go ahead and study those two and see how you did on that. And we'll go ahead and we'll move on into our last example for the day, I believe. And once again, we're back at a mismatch. We had this last lesson as well, and we have it here again. So a mismatch is where I have an axis of rotation, in this case horizontal. And a horizontal requires my functions to be in terms of x. But right now, these are in terms of y. And also, our integral needs to be a dx as well. Okay? Now, if you had a vertical axis of rotation, it would be the opposite. But the reason it's a mismatch is because these functions are in terms of y. And we don't want that. We don't want functions of y. We want functions of x because we're going to be doing a horizontal axis of rotation. And so the solution to the problem is the same as it was last time. Okay? You're going to start by getting the y by itself. I'm going to multiply both sides by 2 first, and then I'm going to subtract 2. So there's my first new equation. So I'm going to use this instead of this. Next, the other equation they gave me was this. First thing I would do is square both sides, which would give me this. And then I would minus 2 on both sides. And now I'm going to use this equation instead of this one. Okay? So when you have a mismatch, when you're rotating around an axis that requires a certain type of function, and the functions they give you are not in terms of that variable, then you need to rewrite those equations. Okay? So let's see here. We have a linear function, which is going to be this guy right here. And then we have a quadratic function, which is a parabola, right? That's going to be this one. And now the question is, which one of those lines are closer than to the dotted line? It's kind of hard to tell on this, in my opinion. But like, let's just pick an x value, like x equals 1. At x equals 1, the green line's here, but the orange line's here. Now, which one of those dots is closer to the dotted line? You could see that it's the orange line is closer than the green line. So the green line is going to give us our big radius, and the orange one is going to give us our little radius. So let's go ahead and begin here. Let's start with our big radius. And now we're back to x, because when you have a horizontal axis of revolution, your functions are in terms of x. So we're going to do function, which is, the green one is x squared minus 2. Sorry, it's crisscrossed. I guess maybe I'll write it over here. Although either way you look at it, it's crisscrossed because I always have been putting the bigger one on the left side so far. Don't want you guys to get confused by that. But we also need to be able to work under diverse circumstances. But anyway, so my big radius is going to be equal to the function that's farthest away from the axis of rotation minus the equation of the axis of rotation. So what is the equation of that line? Well, they tell you at the top it's y equals 2. Right? And I believe we could simplify that a little bit, right? And there we go. There's my big radius. Let's go ahead and find the little radius. My little radius is going to be the absolute value of the equation of the orange line, because it's closer to the dotted line, minus the equation of the axis of rotation. And that would give me a little radius of that. Once we have that, we're ready to go ahead and set up our integral. Pi goes in the front for volumes of revolution. And since we're going with respect to x, we're going to go left to right. So my left endpoint is 0 and my right endpoint is 2. And we're going to do the big radius first. We always do it that way. And then we're going to do the little radius second. And like I said, I wrote them backwards this time, but from what I usually have been doing. But it really shouldn't matter. You should be able to tell which is which and put them in the correct space anyway. And we are integrating with respect to x. Okay. Once again, I would call this one here my y1. I would call this one here my y2. And I would just replace these expressions here with y1 and y2 and go ahead and calculate it out. So let's see what we get. All right, guys, last one I'll have you do is number 10 on your homework. It's a mismatch. These functions are in terms of x, but we're doing a vertical rotation, which means that they need to be in terms of y. So go ahead and pause the video here and see if you guys can go ahead and find the volume of revolution for this particular solid. All right, so here is our final solution here. So first of all, since we're doing a vertical axis of revolution, we need to have our functions in terms of y rather than x, which means we got to get the x by itself, so we have an equation with y in it instead. So I took this one here, and I got the x by itself, so we have an equation with y in it instead. So I'm going to use that instead of this one here. And then that's this green line right here. Now the other equation that kind of creates a boundary here is this red line here. And that's the equation x equals 0. So my big radius is, I've got my colors backwards here unfortunately. This was supposed to be green, this was supposed to be red, but I think I can maybe fix that right now. Let's try it out. Alright, so my big radius is this green line because it's farther away from the dotted line. And that's going to be that green function minus the axis of revolution, which is x equals -2. So we have minus a -2, which becomes plus 2. 1 plus 2 is 3. So my big radius now is that. My little radius is the function 0 minus the axis of revolution, so minus a -2. So it just becomes 2. In other words, the distance from this red line to that black line is 2 spaces. Then we do our washer method volume formula here. And we end up with 10.053. Notice that my limits are 0 and 1 because I'm integrating with respect to y. And the reason I'm doing that is because I have a vertical axis of revolution. And when you're integrating with respect to y, you integrate bottom to top. So that's from y equals 0 to y equals 1. And that'll do it. So I'll leave the rest of them for you guys to do. And we'll say that that is the end in our last calculus lesson of the year. From here on out, we're just doing AP stuff. It doesn't mean we're done by any means. We're going to be sweating bullets here like usual, working hard, but just not learning new material, but just kind of really drilling to get ready for that AP exam for the rest of the year. So well done. Keep it up. We're almost there.